So hello everybody. We are happy to have with us tonight Wen Li. Tonight for us, well, for Wen it's 11 in the morning, right?
Yes, yes.
Boston. So Wen graduated from the University of Science and Technology of China in 2005, and then she moved to the United States for her master's and PhD at UCLA. After working as a researcher at UCLA for a few years, she joined Boston University in 2016 as assistant professor of astronomy. And she's leading now a research group in the astronomy department at Boston on magnetospheric physics. Professor Li has been working extensively on wave-particle interactions in the magnetospheres of Earth and Jupiter, combining satellite observations, theory, and simulation. And she has been involved in a number of very important space missions like Juno, Jupiter, and Van Allen probes and THEMIS in the Earth's magnetosphere. She's very well known in the community for developing a novel physics-based technique to infer Whistler mode wave amplitudes from low Earth orbiting pose-electron measurements. Moreover, she has been using Juno, Van Allen probes, and THEMIS data to provide comprehensive global maps of magnetospheric wave distributions, identifying their key wave properties and calculating particle precipitation that is driven by various magnetospheric waves. She has been a co-leader of a team project on the pulsating aurora at the International Space Science Institute in Switzerland in 2015-2018. And since 2018, she is also an editor for magnetospheric physics with the journal Annales Geophysicae. So Wen, thank you very much for being with us today. And we are looking forward to hear a lot of interesting things about the aurora at Earth and Jupiter, which is also a hot topic these days because of the Jupiter and Saturn conjunction. Thank you.
Okay, thanks so much for your very nice introduction. And I also would like to thank Maria and Yanis for inviting me to give this colloquium and meet the University of Athens group here. And today it's my great pleasure to tell you about the origin of the special type of aurora called diffuse aura at the Earth and Jupiter. And diffuse aura typically occur equatorward of the main oval, and they are not very bright, but they occur very extensively. So at first, I'd like to acknowledge all of my collaborators, as well as the Juno, THEMIS, and Van Allen probes team for their great contributions in this study. So this is my outline, and due to the audience from broad background, I would like to spend a good amount of time giving a general introduction to the Earth and Jupiter's magnetosphere and diffuse aura and discuss why they are important. And then I would like to share with you our current understanding of the origin of the diffuse aura at the Earth. And next, I would like to discuss how we used what we have learned from Earth to understand the diffuse aura in Jupiter's magnetosphere. And last, I would like to summarize the similarities and differences of the diffuse aura at Earth and Jupiter and talk about the exciting future work. So Earth is one of the planets that have a strong internal magnetic field, which can be approximated by dipole. So due to the solar wind and interplanetary magnetic field from the sun, the geomagnetic field lines are compressed on the day side and stretched out behind the Earth, creating a cavity called the magnetosphere, and outer boundary is called the magnetopods. So plasma sheet is a region of closed field lines and consists of hot particles from a few to tens of keV. And in the inner magnetosphere, there exists a dense and cold plasma population extending up to a few Earth radii. And this region is called plasmasphere. So during strong geomagnetic activity, the plasma sheet electrons can inject into the inner magnetosphere, and some of the electrons can further accelerate it to the highly energetic energies and form the Van Allen radiation belts. And some of those plasma-sheet electrons can be precipitated into the dense upper atmosphere and produce the spectacular aurora. So here I listed the air density at the Earth's surface and plasma density in space. And as we can see, the plasma density in space is more than 13 orders of magnitude lower. So the collisions are not important anymore in the magnetosphere, and one of the most efficient ways of changing the particle dynamics is through the wave-particle interaction, as I will discuss in more details later. So this table summarizes key parameters of the Earth and Jupiter. And as we know, the Jupiter is the largest planet in our solar system with a radius 11 times of the Earth. And both Jupiter and Earth have an internal magnetic field, but the surface magnetic field at the equator is more than an order of magnitude larger at the Jupiter than that at the Earth. So therefore, the Jupiter's magnetosphere is huge. And if we magnify Earth's magnetosphere by 40 times, and here is the comparison of the Jupiter's and Earth's magnetosphere. And the size of the magnetosphere towards the sun is around 10 Earth radii at the Earth, but it's up to hundreds Jovian radii for the Jupiter. And on the night side, the Jupiter magnetosphere is even more huge. So if we look up the night sky, and if you could see the Jupiter's magnetosphere, it would be about the size of the moon in the sky, although it's located much, much farther away than the moon. So it's a very, very large magnetosphere. And in fact, from the Voyager mission, we have learned that the Jupiter's magnetotail can extend all the way up to the orbit of the Saturn. So as you can see, it's a really huge magnetosphere. So the trapped particles in the planetary magnetic field experience three types of periodic motion. First of all, particles are gyrating around the Earth's magnetic field. And secondly, when the particle moves towards the higher latitude, the increased magnetic field intensity causes the particle to be reflected and bounce along the magnetic field between northern and southern hemisphere. And thirdly, the magnetic drift causes particles to move in the azimuthal direction. And each periodic motion is associated with a conserved quantity called adiabatic invariant. And a given adiabatic invariant can be violated when the particles interact with the waves with a frequency comparable to the period of their motion. So therefore, the wave-particle interactions play an important role in violating those three adiabatic invariants and changing the particle dynamics in the trapped planetary magnetosphere. So then let me introduce important concept of pitch angle and loss cone. So pitch angle is defined as the angle between the particle velocity and the background magnetic field, and which is given by this expression. So in the previous slide, we discussed that particles can be reflected at a certain altitude as they move from the equator towards higher latitude. And this altitude is uniquely related to the equatorial pitch angle. So we can define an altitude below which the electrons hit the dense upper atmosphere and lost from the magnetosphere, and the corresponding equatorial pitch angle is called the loss cone. So the electrons with the pitch angle right at the loss cone are critically trapped. And whereas electrons with pitch angle smaller or are greater than the loss cone, they remain stably trapped by bouncing back and forth between the northern and southern hemisphere. However, electrons with pitch angle smaller than the loss cone like this, they can precipitate into the upper atmosphere and through the collision with these dense neutrals there, and thus are removed from the magnetosphere. So this process is an important loss process for the trapped particles in the magnetosphere. And in fact, some of these electrons can produce the spectacular aurora by hitting with the dense neutrals in the upper atmosphere. So this movie is taken from the front of the International Space Station as it orbits the Earth, which is quite spectacular. So as we can see, the aurora take place in various forms, and those sharply defined structures are the so-called discrete aurora, but there are also some unstructured glow in the sky, which we call as a diffuse aurora. And let's look at it again. And if we look carefully, and we can see that some of the diffuse aura, like this one, are pulsating by switching on and off, and called a pulsating aura. So in this talk, we'd like to focus on discussing the diffuse aura as well as the special type of diffuse aura, pulsating aura. So this is the aura observation from the International Space Station, and all sky imagers installed on the ground also provide an excellent opportunity to visualize the aura evolution on a global scale. So this is the THEMIS all sky imager network, which consists of 20 ground cameras at stations throughout the North America. So in this movie, as we can see, the diffuse aura is a belt of relatively weak diffuse emissions extending equatorward of the aura oval. And we can see that some dynamic structures embedded in diffuse aura are pulsating. And this is pulsating aura, which we just discussed. So how is aura generated? So since this is a key concept in this talk, I'd like to spend a little bit of time introducing the basic generation mechanism of aurora, which is shown in this movie very nicely. So those precipitating particles with energy between like a few and tens of keV move along the planetary magnetic field line and then collide with the neutral atoms in the upper atmosphere and cause them to the excited state. And then those excited atoms will emit light to produce the aurora by returning from an excited to the ground state. And aurora can be several different colors, like greens or purples or red, but the color depends on which atom or molecule is excited by the impact precipitating particles as well as their energy. So the most common aurora color is, as we know, is green, which comes from the excitation of atomic oxygen. And then the next question is, what do cause electrons to precipitate into the upper atmosphere? So as I mentioned before, when the electron pitch angle is small enough to fall into the loss cone, then electrons can move along the magnetic field line all the way to the low altitude and ultimately precipitate into the upper atmosphere. So in the basically collisionless magnetosphere, in order to be scattered into the loss cone like this, the electrons need to interact with the waves. And those efficient wave-particle interaction occurs when they satisfy this resonance condition. That is, the Doppler shifted wave frequency is equal to the multiples of the relativistic electron gyro frequency. So if we take electrons and the right-hand polarized wave as an example, and when this resonance condition is satisfied, these gyrating electrons and waves are locked in phase over many, many cycles and have time to interchange their energy and momentum. So this resonant wave-particle interaction can cause an efficient pitch angle scattering of particles and precipitate them into the upper atmosphere. And this movie is an example showing how those trapped electrons can be lost to the upper atmosphere through pitch angle scattering. So those are the trapped electrons indicated by red color, and this white is the waves. And then through the interaction, you can see the trapped particles can be lost into the upper atmosphere. So why are diffuse and pulsating aura important? So although the diffuse aura emissions are weaker than the discrete aura, the global distribution of diffuse aura precipitation supplies over 70% of the precipitation energy input into the upper atmosphere and leads to the enhanced ionization and chemical changes there. At the same time, it also changed the ionosphere conductivity that provide a strong coupling between the magnetosphere and the ionosphere. The diffuse aura is also commonly observed at Jupiter. And this figure shows a typical example of Jupiter's aura from the Hubble Space Telescope. And Jupiter's aura consists of three main components. This is the main oval, which is very bright and narrow, and indicating the circular features. And then these little dots with the tails are the satellite aura spots, which correspond to the footprints of the magnetic field lines connecting the Jupiter's ionosphere with those largest Galilean moons, which is Io footprint and Ganymede footprint is Europa footprint. And then those emissions are transient polar emissions, which are relatively poorly understood at this stage. So in this study, we're going to focus on this emissions, diffuse aura, which extends from the all the way from the main oval towards the lower latitude, and occasionally forming like a discrete belts or patchy irregular emissions. So Jupiter's aura is hundreds of times more powerful than that on the Earth, and that's also why it's so interesting to understand their drivers. And unlike these on the Earth, the aura at Jupiter are permanent and rotate with the planet, so we can always see the aura at Jupiter regardless of the solar wind conditions. And Jupiter's aura have been observed in almost all parts of the electromagnetic spectrum, including like radio waves, infrared, and visible ultraviolet, and even soft X-rays. So in this talk, I'd like to discuss the similarities and differences regarding the Whistler mode waves and diffuse aura at Earth and Jupiter through addressing those following specific questions. So where do diffuse aura emissions occur? And what is the energy range of particles powering diffuse aura? And what is the driver of diffuse aura? Okay, then I'd like to move on to the next section to discuss the diffuse aura at the Earth, followed by a more detailed discussion at Jupiter, including our latest result later. So where do diffuse aura emissions occur at the Earth? So based on the 11 years of DMSP satellite observations, Newell et al. Showed that the diffuse aura energy flux as a function of a magnetic latitude and the local time. And this is how the aura distribution look like if you view it from above the North Pole. So in this coordinate, the sun is on the top. And the top and bottom panels are for lower and higher solar wind conditions. So as we can see, the diffuse aura at the Earth mostly occur over like a pre-midnight to the noon sector. In terms of latitude, it's between 60 and 68. And if you map it all the way to the magnetic equator, then it's corresponding to the L shells from like 4 to the 12-ish. And as we can see, by comparing the two different solar wind conditions, the energy flux increases by at least a factor of 3 from low to the high solar wind driving conditions. But also, interestingly, during higher solar wind driving, the diffuse aura region extended to lower and higher latitude. So it's become more extensive during higher solar wind driving conditions. So although both ion and electron precipitation contribute to produce diffuse aura, the average number flux and energy flux of precipitating ions is typically 1 or 2 orders of magnitude less than that of precipitating electrons. So therefore, electron precipitation play a dominant role in driving the diffuse aura activity at the Earth. So the next question, what is the energy range of electrons powering diffuse aura? So the conjugate observation between the aura observation and particle measurements at low altitude answered this question. And this figure shows the aura measurements when a Remissions satellite is passed through. And this black line represents intensity at the foot point location extracted from this optical signature. And those 3 color lines represent the sound flux of downward going electrons over those 3 different energy ranges. And blue line represent around 10 keV electron precipitation, which matches pretty well with this optical intensity. And the bottom panels show the energy spectra for the downward trapped and upward going electrons. And again, supporting that electron precipitation, from like a few to 10 keV is consistent with the observed enhanced aura intensity. And here's another example. And this panel shows aura measurements when the fast satellite passed through. And if we look at the pitch angle distribution, when the satellite was inside the diffuse aura region, we found the nearly full loss cone distribution here in the downward going direction with almost empty loss cone in the upward going direction. And the low energy boundary is found to be extend to the even down to 500 eV at higher L shells. So as we can see, the energy range of electrons corresponding to diffuse aura precipitation is from several hundred eV all the way up to a few tens of keV at the Earth. So then the next question is, what is the driver of the diffuse aura? So pitch angle scattering by magnetostrip waves have been suggested to be the potential candidates, particularly the Wither mode chorus waves. And let me briefly introduce what are the Wither mode chorus waves. So Wither mode waves are the electron cyclotron wave with frequency between the proton and electron cyclotron frequency, and they often exhibit two distinct bands, a lower band and upper band. And if we look at their wave fields in a plane perpendicular to the wave vector, we can see that they are right-hand polarized wave. And this figure shows the Wither mode waves in the frequency time spectrogram in electric and magnetic field. And we can see they often show those kind of a discrete coherent structures, such as the rising tones and sometimes even the falling tones. And then if we play the wave signal through the audio converter, then it sounds like a bird's chirping, right? As shown in this example observed in the Earth's magnetosphere. And that's why this wave is also called the Wither mode chorus waves. So what is the driver of diffuse aura at the Earth? And to identify the driver, we took advantage of the conjugate measurements between the THEMIS D and all-sky imager. And as shown in the wave spectra in the equatorial magnetosphere, the chorus waves are modulated. And this right panel shows the aura measurements during 1, 2, 3, 4, 5, 6, corresponding to these 6 particular time snapshots. So as you can see, this is the broad diffuse aura emission. And as you can see, when the chorus waves intensify like a 1, 2, the diffuse aura emissions also become intense, and it becomes weaker when the waves are also weaker. Okay, so showing almost a one-to-one correlation. And then the next step is to calculate, to quantify electron precipitation driven by the chorus waves. So let me briefly introduce how we quantify electron precipitation driven by wave-particle interactions based on the quasi-linear theory. So as I mentioned before, when the waves and particles satisfy this resonant condition, electrons can experience a pitch angle diffusion, and some of them are scattered into the loss cone. So for a given wave frequency, based on this equation and the dispersion relation, we can calculate the local pitch angle diffusion coefficients. And as particles move along the field line, and due to the changes in the wave and plasma parameters, the resonant condition also changed correspondingly. So what we do is we took an integral over the field line to calculate the bounce averaged diffusion coefficients. And this figure shows a normalized electron pitch angle distribution. And this vertical black line is the bounce loss cone here. So as you can see, as diffusion coefficient increase, the loss cone become more and more filled. In other words, more and more electrons fall into the loss cone and precipitate into the upper atmosphere. So from this pitch angle distribution profile near the loss cone, we can calculate the precipitating electron fluxes for any given energy of electrons. So using this approach, for the previous diffuse aura event, we calculated the pitch angle diffusion coefficients due to the observed chorus waves. And these are the two examples during 2 different snapshots when the waves are strong and weak. And so based on the plasma sheet electron observation from THEMIS and the calculated diffusion coefficients, we can estimate the characteristic energy of precipitating electrons and their associated total precipitating flux, which are shown in those 2 panels. And then we can use the empirical relationship to further estimate the diffuse aura intensity and compare with the observation, which is shown here. So we can see that the modeled diffuse aura electron precipitation, is the red line, agrees very well with the observed aura intensity, black line, and providing convincing evidence that chorus scattering is the dominant driver for the diffuse aura electron precipitation. So this is a case study, and in addition to chorus waves, another type of wave called the electrostatic electron cyclotron harmonic wave, ECH wave, is also known to contribute to the diffuse aura electron precipitation. And those waves occur typically above the electron cyclotron frequency, showing those harmonic structures. The left figure shows the statistical distribution of diffuse aura electron precipitation. ECH wave and the chorus wave intensity, categorized by different levels of the geomagnetic activity from weak to strong. And as we can see, all three of them depend on geomagnetic activity, and considering the sun is on the top, they're typically strong from pre-midnight to the noon sector, showing very similar features. So through quantitatively estimating the diffuse aura electron precipitation, we found that in the inner magnetosphere, the less than L shell of 8, the chorus is the dominant mechanism. However, in the outer magnetosphere above 8, the ECH waves are the dominant mechanism of driving this diffuse aura at the Earth. Okay, so far we went through the diffuse aura in the Earth's magnetosphere, and next I would like to discuss the diffuse aura at Jupiter to see if we can apply what we have learned at the Earth to better understand the diffuse aura at Jupiter. So let's first consider the question of where the diffuse aura emissions occur at Jupiter. So this figure shows an example of the aura intensity observed by the Hubble Space Telescope in the northern and southern hemisphere. And this white dashed region represents the diffuse emissions, which occur equatorward of this main auroral oval. So this is a main auroral oval, and this is Io footprint. And we can see these diffuse emissions occur between Io footprint and equatorward of this main oval. So based on the 10 years of the HST data from like 1997 to 2007, the diffuse aura is found to be almost always present, and particularly in the dusk sector at Jupiter. So this figure shows an interesting event, and where the HST observed the diffuse aura and Galileo satellites moved to the conjugate location, but near the equatorial plane. And here, this red dot represents the footprint of the Galileo satellite. And this figure shows the Galileo satellite trajectory in the equatorial plane, moving from closer to the farther away from the planet. So here, this green region represents the green region here. And if we look at the electron pitch angle distribution, we can see at less than 17 Jovian radii, the Galileo observed like a pancake distribution with the flux peak around like a 90 degree here. But at the higher M shells, above like 18 or so, they start to see those kind of a bidirectional electron pitch angle distributions. And interestingly, at this region, when they see this pancake distribution, Galileo also observed the Whisper mode wave emissions. So based on these conjugate measurements, this study suggested that diffuse aura is caused by the pitch angle scattering of Whisper mode waves at Jupiter. However, since the loss cone is very small at the equator, as you can see here, it's very difficult to tell if those electrons are really precipitating into the atmosphere and produce the aurora. So due to the limited observations, our understanding of Jupiter diffuse aurora is much more limited than that at the Earth, until we have the Juno mission up. So let me briefly introduce the Juno mission, since we're going to use this data to show us a couple of interesting studies recently. So Juno is the first spacecraft to explore the polar region, where the auroral currents flow and particles are accelerated and radio emissions are generated. So as you can see, the perigeo of the Juno is really close to the planet. It goes like a 1.06 RJ, and the apogee is very far away, above 100 RJ. And in particular, Juno mission provided an excellent opportunity to study the precipitating particles producing the various aura emissions, including diffuse aura. So Juno is equipped with a high quality, the particle and magnetic field, as well as the wave instrument, and also several instruments to measure aura emissions, including the infrared and UV, as well as the high quality camera, JunoCam, that will tell us about the aurora and their controlling processes. So the instrument we will primarily use in this study is the UVS to measure the auroral intensity and false color map, and also JEDI and JADE to measure the particle flux as well as their pitch angle distribution all the way from 100 eV up to 1 MeV, and the wave instrument to measure the plasma wave intensity in both electric and magnetic field, and the magnetometer to measure the ambient magnetic field intensity. So Juno has started to orbit around Jupiter since July of 2016, and with the orbital period around 53.5 days. And currently it has orbited around Jupiter about 30 times so far, and it will continue to orbit over the next few years, at least. So where do diffuse aura emissions occur at Jupiter? So this figure shows the UVS aura observations during the perigee 1, the first perigee pass in the northern hemisphere, showing the intensity on the left and the false color map on the right. So the bright emission here, this one is the main oval, and we can see these diffuse aura emissions observed over a broad range, equator world of the main oval. And these false colors provides a way to visualize the attenuation of the H2 aura emissions by Jupiter's hydrocarbons, with more reddish color representing aura emissions below the Jupiter's homopods, and in other words, indicating more energetic particle precipitation. And the green line here represents the Juno footprint. So we'll focus on the diffuse aura region here, where the Juno flew through. So if we look at the false color map, there are two discrete bands with the reddish color located equatorward of this greenish color, indicating that the precipitation of more energetic particles occur equatorward of the less energetic particles. Then let's look at what Juno measured in situ for particles and waves along the satellite trajectory. So this is the Juno trajectory in the XZ plane, and Juno is moving from higher to the lower latitude towards the equator. And this one also shows the Juno trajectory if we view it from above the North Pole. So here the two red dashed lines represent the inner and outer boundary of the main oval from the statistical results, according to this. And in the left figure, from top to bottom, it shows the electron energy spectrogram in the high energy and lower energy and their corresponding pitch angle distributions. And the bottom two are the frequency time spectrogram and wave, electric, and magnetic spectrum. So as we can see that when the Juno move over the statistical main aura oval, like this here, it first observed upward going electron beams at higher energy and then at lower energies. And at the same time, it also observed the intensification of broadband waves. And later on, as Juno go further equatorward, they observe a completely different pitch angle distribution. And as you can see, the lost cone is almost filled, indicating electron precipitation, but very few electrons are moving upward in this region. So let's look at this feature more carefully. So as we can see, that at the higher latitude, Juno observed upward going electron beams, and then the pitch angle distribution exhibit a full lost cone here. And this is a clear signature of the electron precipitation caused by the strong diffusion. So we identify this region as the diffuse aura region, but we do notice that more energetic electron precipitation is confined to the lower latitude than less energetic electron precipitation. So if we look at the plasma waves at the same time, intensification occurs mostly below the proton spectrum frequency, but there is no clear correlation with the precipitating electrons, and suggesting that the waves driving pitch angle scattering are probably located near the equator, not at such high latitude like 65 degrees. So the L shells corresponding to this diffuse aura region are around like between 9 and 18. And then in order to visualize the comparison between the electron precipitation and auroral emissions more clearly, here we plotted them together. So the precipitating electrons within the loss cone are calculated for lower energy and higher energy separately, but with the same color bar. So we can see that lower energy electron flux peak at the higher latitude than that of this kind of higher energy, and which is consistent with the false color map plots, where more energetic electron precipitation was observed equatorward of the lower energy electron precipitation here. So this provides the direct evidence that diffuse aura at Jupiter is produced by precipitating energetic electrons in a broad energy range, all the way from 100 eV up to the 1 MeV. Then let's look at the next question. What is the driver of diffuse aura at Jupiter? So to address this question, we performed a quantitative analysis of an event. So we took advantage of the coordinated observation between electron measurements at low altitude, where the loss cone is big enough to be resolved, and then the wave measurements by the waves instrument near the equator. So they're connected by the almost the same magnetic field line. So in this figure showing the UVS aura measurements, we can see these diffuse aura emissions were observed equatorward of the main oval, as expected, and Juno was passing over this diffuse aura region. And let's see what they observed. So here is the pitch angle distribution measured by JADE and JEDI all the way from 100 eV up to the 350 keV, when Juno was passing from lower to the higher M shells at a low altitude in the northern hemisphere. So here the dashed black lines represent local bounce loss cone, indicating downward going electrons and the upward going electrons. And we can clearly see this kind of a asymmetric pitch angle distribution with the filled-in loss cone features in the downward going direction and almost empty loss cone in the upward going direction. So when Juno was passing in this region from M shell around from 8 to 15. However, at low energies like 100 eV and 1 keV, the electron flux inside the loss cone is actually even higher than that outside loss cone, which is unlikely caused by the wave-driven pitch angle scattering alone. However, at the higher energy above 10 keV, we can see that the electron flux inside the loss cone is similar to that outside, which is consistent with the wave-driven pitch angle scattering effects. So to understand the drivers of causing this electron pitch angle scattering, we really need to know the wave distribution along the field line all the way to the equator. So here is the summary plot showing the wave measurements and in the equatorial plane together with these electrons at a similar M shell around 10, but this observation is taken like a few hours earlier. So in this region, the JEDI observed this kind of a pancake electron distribution peaking at 90-degree pitch angle, which is probably unstable for the Whistler wave generation. And at the same time, the waves instrument observed the strong Whistler mode waves. It's like pretty similar to the chorus waves at the Earth. And we took the wave spectra averaged over this particular period, which is corresponding to the M shell around 10, and use this to evaluate the effects on the electron precipitation. So this chart shows the steps to calculate the electron precipitation due to Whistler waves. So at first, we need to know the Whistler wave properties along the magnetic field line. And we obtained this from our recent statistical study from the combined Juno and Galileo observations. So this figure shows the Whistler wave amplitude as a function of M shell and the latitude. And as we can see, the Whistler wave power is relatively strong over the M shell between 8 and 13. And it's an important feature is that the strong Whistler wave power can extend all the way up to at least 50 degrees of magnetic latitude. So we use this input to calculate the pitch angle diffusion coefficients. And then which is further used to estimate the electron pitch angle distribution near the loss cone, as we discussed before. And then this electron pitch angle distribution inside the loss cone is used to estimate the precipitating electron flux at various energies. And then these theoretical calculations can be compared to the particle measurements from Juno, as well as the diffuse aura measurements by the UVS. Okay, and let's look at the quantitative calculation for this particular event. So here, this is the bounce average, the pitch angle diffusion coefficients calculated at around M shell around 10.3 as a function of pitch angle and energy. So as we can see near the bounce loss cone, the diffusion coefficient is strong from like a tens of keV all the way up to the 1 MeV. And then if we compare the calculated diffusion coefficients indicated by this black line to the strong diffusion limit, we can see that diffusion coefficients is comparable or even larger than the strong diffusion limit at energies above 10 keV, but it's much weaker at lower energy. And then let's look at the comparison of electron precipitation from observation and model. So this figure shows the observed electron pitch angle distribution using solid lines, and the model results inside the downward loss cone using the dashed lines calculated for different energies. So as we can see, the calculated electron precipitation due to Whistler waves is very consistent with the observation at the energy above 10 keV. So however, at lower energy below 10 keV, the model underestimates the observation, suggesting that additional mechanisms are needed to precipitate the less than 10 keV electrons. So here I only show the calculation at one particular location at 10.3, but we actually extended the calculation to a broader region of the radial distance and found a similar conclusion. Okay, now let's briefly summarize the findings of origin of the Jupiter diffuse aura. So I shared with you two studies regarding this, and what we found is that so using coordinate measurements of particle and aurora from Juno, we provided direct evidence that the precipitating energetic electrons over a broad energy range are mainly responsible for generating diffuse aura emissions at the Jupiter. And we also used the quantitative analysis based on Juno observation and quasi-linear theory to find that the Whistler mode waves as a primary driver for like above 10 keV electron precipitation leading to the Jupiter's diffuse aura. But we also found that additional mechanisms are needed to account for the electron precipitation below 10 keV. And then I would like to use this table to summarize the similarities and differences of Whistler waves and the diffuse aura at Earth and Jupiter. So this is the three questions we raised at the beginning. So where do diffuse aura emissions occur? So at the Earth, they typically occur at the L shells between like 4 and 12, and they have a strong MLT preference from pre-midnight to the noon sector. At Jupiter, they occur in a more extensive region up to the 18. But MLT dependence so far is not very clear since we still have a limited coverage in MLT. And then the second question is, what is the energy range of particles powering diffuse aura? So at the Earth, the energy, the upper limit of energy is lower, up to like a 10th of keV. But at Jupiter, it could be up to the 1 MeV. So it's a much broader energy range. And then what is the driver of diffuse aura? So at the Earth, we think we have a good understanding, and we think cores play an important role at L shell less than 8, but ECH waves start to become more dominant at L shell above 8. So at Jupiter, there are still outstanding questions, and what we have learned so far is that the chorus wave, the Whistler mode waves play an important role in driving the electron precipitation above 10 keV in this region. But like other mechanisms, like ECH waves or even other mechanisms are probably needed to account for the electron precipitation at lower energy and also probably in other regions. Okay. At last, I would like to briefly discuss the open questions and the future work regarding this topic. So we believe we have a pretty good understanding of the characteristics and origin of the diffuser at the Earth. And then the next question is how to model the observed diffuse aura electron precipitation on the global scale under various levels of geomagnetic activity. So this will be really helpful for modeling the magnetosphere-ionosphere coupling, since diffuse aura precipitation plays an important role in changing the ionosphere conductivity. And I haven't really had much time to discuss the special type of diffuse aura, pulsating aura, but there are some interesting open questions regarding pulsating aura, such as what is the spatial size of the pulsating aura and how do they vary at different locations? And what does control the modulation of pulsating aura? And regarding the Jupiter, there are more open questions. And for example, what is the statistical distribution of Whistler waves and diffuse aura on a global scale? I think we have done this for the M shell and the latitude, but so far, due to the limited MLT, we don't really know about the MLT dependence. And in particular, we'd like to know if there is any asymmetry in MLT, like what we found at the Earth. And also, we mentioned that although the Whistler mode waves are primary driver at higher energy electron precipitation at a certain region, but there could be other drivers which can account for the diffuse aura generation at lower energy and in other regions. And we would like to see what are those potential mechanisms, or what are their quantitative contribution. Okay, so thank you very much for your attention, especially right before this holiday break. So I will stop here to answer your questions, if any.
Thank you very much. It was a very interesting talk.
Thank you.
With a lot of information.
Yes, yeah, probably.
No, thank you. This was very interesting. So I think that, yeah, we have plenty of time for questions. And so I would urge any people that have questions to ask them now. They can raise their hands or they can unmute themselves, whatever you prefer.
Maybe if there is nobody yet, maybe I could ask a couple of questions. Yeah?
Yes, of course. I don't see any question now.
There is one question I see.
There's one question. Okay.
Shall I read? What other
yes, of
what
course.
other mechanisms seem responsible for the lower energy precipitation that weren't included in the model?
Okay, yeah, that's a really good question. So let me go to the slide. Okay, so if you look at their pitch angle distribution, at lower energy, as I pointed out before, the electron flux inside the loss cone is even higher than outside loss cone. So remember, this is the loss cone, the black line is loss cone. So inside is higher than loss cone. But this is the mechanism we wouldn't expect just from the wave-driven scattering, because for a wave, they're scattered from higher to lower pitch angle. So we would expect to have a smaller or similar pitch angle distributions if it's driven by the waves. So for lower energy, based on this feature, we think it's probably relevant to more like a field line acceleration. So, but we don't know the exact detailed mechanism causing this field line electron acceleration. But one thing I can clearly see is that it's different from higher energy, which is consistent with this wave-driven feature. So probably in like a electric field along the field line, which may be responsible for accelerating those lower energy electrons. But yeah, I think further studies are needed to confirm if this is true or not.
So
Okay.
maybe you can go ahead
Yeah.
with your
Okay.
question.
I have a couple of questions. When I haven't seen many pictures, many pictures of the Jupiter aurora, and I wonder if the main oval on Jupiter is always as narrow as we have seen it in the couple of pictures that you showed.
So main oval is a relatively stable feature because it's caused by the co-rotation breakup. So Jupiter is a rapidly rotating planet, and because of that, you need really high energy to to maintain this momentum. But at some point, at a certain radial distance, the co-rotation will start to break. And in order to maintain those co-rotating particles, the radial current has to flow, and those radial current has to close. So that's why the field line currents associated with radial currents start to flow to produce this main oval. And let me try to go back to the main oval picture. Yeah, so this is a main oval, and this main oval is relatively corresponding to the L shells, like a 20 to 50-ish. So in terms of M shell region, it's not really narrow, but this is the region where this co-rotation break up, and this is internally driven. So it's not dependent on the external drivers like solar wind. So that's why they're relatively steady and fixed in the similar region like this. However, like other, the aura, like polar emissions, they're highly variable, and some studies found that those emissions are responding to the solar wind dynamic pressure. So associated with higher solar wind dynamic pressure, and some studies shows increased polar emissions. But for main oval, it's relatively stable and fixed.
Okay. And maybe I can ask one more. Do we have information about any MLT dependence of chorus emissions at Jupiter, or do we have enough observations to say anything about that?
And that's a really great question. So let me try to find one slide to address that. So this is the statistical distribution of chorus waves from Galileo spacecraft. So the Galileo spacecraft, they spend a good amount of time near the equator, but as you can see that MLT coverage is still very, very limited. So this one shows the chorus wave power, and this is a current rate, but you can see some gaps there. But just from the Galileo satellite, we can see that the MLT dependent in terms of current rate is not that strong. And as Earth has a pretty strong asymmetry with much stronger wave amplitudes on the night side, night side to noon side compared to here. But at least at the Jupiter, from this limited coverage, we didn't see that strong dependence. And that's from Galileo. And for Juno, so far it covered from dawn to the midnight. This is MLT, and this is sun, and so this is midnight. So far it's covered here, and later on, Juno will continue to cover the dusk side. So hopefully by combining the Juno data, including the upcoming data, we probably have a better idea on the MLT coverage. But in terms of MLT dependence, I think the less dependent feature is actually somewhat expected at Jupiter, because the generation mechanism with the fundamental mechanism is similar, but at Jupiter, like injection events and interchange instability are more responsible for providing those free energy for Whistler wave excitation, and those can occur in any MLT, not necessarily starting from the plasma sheets from the night side and then move to the later MLT. So those, because Jupiter is pretty much internally driven, it's very different system at the Earth, which is highly connected to solar wind from the tail and the injection, but Jupiter is more rotation dominated, and because of that, the MLT dependence is expected to be weaker than that at the Earth.
Thank you. And although I had the impression that there is some slight asymmetry in the Galileo data towards the dusk.
Yes, yeah. So I think the authors, this is the asymmetry they mentioned, but they also mentioned that here the coverage is much less. I mean, there are much less number of samples in this MLT compared to this. So they're not quite sure about the statistical significance of this data. So they have some they mentioned this caveat in their paper. So yeah,
Okay.
hopefully we can confirm this.
So it's not normalized according to observation coverage, so to speak. Okay, I see some written questions. Let me read. Wouldn't it be more conclusive to compare with Saturn's aurora because of the similarities of the two planets?
Yes, this is a good question, but this actually depends on my background. So I started my research from the Earth's magnetosphere. That's what I spent all the way from like my PhD study, starting from 2005 to throughout the Van Allen Pro's mission until last year. And then I started to become more involved in the Jupiter, starting with this Juno mission since 2016. So I started from the Earth's magnetosphere, and then I'm expanding my research to the Jupiter to try to see their similarities and differences. So that's why I present in this way, but I agree that since the Jupiter and the Saturn, they are both like giant planets and they're both highly magnetized. So there should be a lot of similarities there. So if you talk to the more planetary people who study both like Saturn and Jupiter, they probably give a much better perspective on the similarities and differences for Jupiter and Saturn. And I'm very interested in learning Saturn's aura as well, but I'm not expert right now. Yeah.
Okay, there is one more question from George Vasilopoulos. Thank you for the very interesting talk. I have a question about the detection of 11-minute X-ray pulsations from the South Pole only. Is this related to some physical time scale, wave propagation time? And do you have any ideas why we only see them from one of the poles?
Oh, you mean the Earth study? Okay, let me try to go back. So I believe you're referring to this one. Is it correct? Let me know if it's not. Yeah.
Maybe he can. Maybe George, you can clarify what you mean.
Hi. Yes, I remember there was a paper like a couple of years back where there was detection of X-ray pulsations from Chandra and XMM in combination with Juno data, where they
I see.
Where they had found that the aurora was actually pulsating on the South Pole, I believe, and this had. So I was just curious if this is related to the kind of work and what you presented, that if there can be any connection between the time scale of that periodicity and the wave propagation time.
That sounds like a very interesting study, which I am actually not aware of. So I think you are talking about the Jupiter's aura, right? So
yes, for Jupiter. Yes.
Recorded the 11-second modulation. So I think I probably need to know which aura they're talking about, because as I mentioned before, Jupiter's aura, they have several different kinds, including the polar emissions and all sorts of things. So if they are talking about these diffusive emissions equator of the main oval, I think based on what we have learned at the Earth, like the chorus, the Western mode waves could be modulating on a time scale of like a few to tens of seconds, then it could be responsible for producing such kind of pulsating aura at Jupiter. I wouldn't be surprised to see that. But if they are talking about some other emissions, like a polar emission, then that's a completely different story. And currently, we have a very limited understanding on the generation of polar emissions right now. So yeah, I would be very interested in looking further into that paper to see which aura they are referring to.
I think the paper was done et al. 2017, and
Okay.
they were referring, I think, to only to the polar emission.
Oh, yeah, only to the
Yeah.
polar emission. Yeah, the polar emissions is a very intriguing and but mysterious target right now. Yeah, a lot to learn from there.
When may I ask, polar? Wouldn't we expect maybe polar emissions to be related to a source that would be outside of the Jovian magnetosphere?
Could be. Yeah.
Through open field lines, maybe. Well, just guessing.
Yes, yeah. I think that's a very reasonable guess because, you know, there is still debate about the open-closed boundary at the Jupiter's magnetosphere right now. But what I understand is that the polar emissions is found to be somewhat correlated with solar wind driving. So which means that they are more relevant to external drivers compared to like this you know, the moon footprint or the main emission. They're mainly, you know, internally driving, right? But polar emissions, yeah, it's probably more relevant to the external drivers through the solar wind. Yeah.
Okay. Okay, one more question. He's a rather naive question. What causes the Corus-Whistler waves? And what observational properties, for example, properties of the solar wind, may correlate with the intensity of the diffuse aurora throughout the solar system?
Okay, yeah, this is actually pretty a good question. So, so how the Corus waves are generated? So let me see if I can find the figure. Okay, I probably didn't include in this presentation, but I would like to say that when I discussed this, the first magnetosphere picture, so the plasma sheet electrons, when during active times, they can inject into the inner magnetosphere, and when they you know, transport into lower lower L shells, then the pitch angle distribution start to become more and more anisotropic, which means that you know, through the beta Chern acceleration and the Fermi acceleration, they are accelerating both perpendicular and parallel direction, but they're accelerated more in the perpendicular direction. So because of that, then they start to develop those kind of a pancake pitch angle distribution with the peak flux at 90 degrees. So this is so-called anisotropy. So perpendicular temperature is larger than the parallel temperature. So this kind of electron distribution is unstable, and this can provide a source of free energy for Whistler wave generation. And as you can see, in terms of their correlation to solar wind, if there is a higher solar wind activity, let's say stronger southward BZ and stronger solar wind velocity, and then they're gonna you know, lead to the stronger convection, which can more effectively bring those tail particles into the inner magnetosphere and develop an increased number of energetic electron population, which can provide an increased source of free energy to generate the Corus waves. So they are indeed relevant to the highly relevant to the solar wind, and through those you know, through changing the plasma sheet particles and how much of them they can be injected into the lower L shells and generate the Corus waves in the inner magnetosphere. So I hope this answers your questions and the diffuse aura throughout the solar system. Throughout the solar system, yeah, I can't speak about throughout the solar system, but based on what I have studied for Earth and Jupiter, yes, at the Earth, it's highly relevant to the solar wind. I mean, for both Corus and the diffuse aura. And Earth, I have shown that, right? They are highly relevant to the different levels of the geomagnetic activity. And as shown in this particular figure, the low to the high activity, you can see this increased level of diffuse aura as well as waves in the similar way. At the Jupiter, the solar wind dependence is not well known right now because, you know, at the Jupiter, we don't have this luxury solar wind monitor all the time, you know, like we have at the Earth. So we don't really know about the exact solar wind conditions at the Jupiter to study this solar wind dependence yet. And hopefully in the future, yeah, there are some very nice, you know, Jupiter missions coming up, like Europa Clippers and JUICE, and that's the East Side Relevant mission, right? JUICE. And yeah, hopefully all those missions coming up in together will help us address those questions.
Okay, and this is Maria's question. She's wondering why the energy range of electrons powering Jupiter's aurora is much wider than the one of electrons powering the Earth's aurora.
Yeah, that's a really great question. So remember, Jupiter has a much larger magnetosphere with a much stronger magnetic field. So, and Jupiter, because of that, Jupiter could accelerate electrons to the much higher energy. For example, for radiation belts, you know, at the Earth, maybe it's up to 10 MeV electrons. But at Jupiter, it could be more than 100 MeV electrons. So because of this different system, the size of the system, as well as their strong magnetic field, the particles can, you know, accumulate their energy to a higher energy range. And that's why now when we look at the particle spectra at the Jupiter, there are much higher energy tail going on at the Jupiter compared to the Earth. And so in that sense, the energy spectra, which probably need to shift, you know, to the higher level when we consider the similar type of particle distribution at the Earth versus the Jupiter. So I think, yeah, this is relevant to the why, you know, the electrons powering Jupiter's aurora has a higher energy limit. And that's a really great question. So for example, the inverted B we saw at the Earth is around like a 10 keV or so, right? Inverted B corresponding to the parallel acceleration. At Jupiter, it could be more than several hundred keV. So for all of those energies, if we think about and compare them side by side, their energy is larger, including radiation belts, auroral acceleration, as well as those inverted B, that type of thing. Yeah.
Okay, thank you. Yes.
I guess you have a larger abundance of much higher energy electrons at Jupiter, right?
Yes. Yeah. And we're really interested to understand how can, you know, electrons be accelerated to the 100 eV or more at Jupiter, which is the most efficient accelerator in our solar system.
Great. So I don't see any other question. And I think we are very happy. That was a great talk, Wen. Thank you very much. Very, very informative.
Yeah, thanks so much to give me this opportunity to interact with you. And it's also my great pleasure. And Merry Christmas and Happy New Year, everybody.
Thank you.
Yeah.
Thank you.
Thank you.
Yeah, bye
Merry
everyone. I hope to see you someday.
Hopefully soon. So stay safe and